Hi guys, and welcome to Learn Extra Live. This is Physical Science, grade 11, and finally it's your turn. I know that there are grade 12s tuning in too, and I'm Indiana, and as you can see, Bruce is with me today. Hi, Bruce.
Indy, how are you doing?
Good, much
Excellent.
better, yeah.
Great, good. Nice to see you again.
Yeah, I know. I haven't been on forever, hey?
I know, you've been missed.
You guys,
Yes,
but you guys better have missed me, hey? So what are we chatting about today, Bruce?
Indy, what we're going to be having a look at today is we're going to be looking at acid-base reactions. Now, if the grade 12s have tuned in, guys, it's a very good revision for you because there can be a couple of things that can sneak into your grade 12 exams associated with acids and bases. So it might be good revision for you guys. The grade 11s, we're going to go over some of the basic concepts of acid-base reactions and also some quite nice little quirks along the way. So
That's
be good to tune in and watch.
Yeah, okay, cool, guys. So you guys better be watching us. Bruce, you can take your
can I give you
stations.
my state? Great.
Yeah, while he's doing that, guys, all I do is chat to you and tell you to join us on facebook.com/Learn Extra. Also chat to me on Twitter at Learn Extra. If you have any questions, don't forget that we will be answering them in the last 15 minutes of the show. Also, please try and make sure that they are related to the topic that we are going over. And without further ado, I can see Bruce is ready for us. Take it away, Bruce.
Great, thanks, Indy. Well, guys, welcome back. And what I've got here up on the board, and as you can see on the template, we're going to be looking at acid-base reactions. Now, the concept of acids and bases is something that's not unfamiliar to you. You've probably heard about acids in everyday life. You've spoken about bases in everyday life, and you probably referred to them all through your school career. But what we're going to do today is we're going to focus a lot of attention on the specifics of acids and bases, and we're going to look at now how unique these particular acid and base molecules are. In other words, what I'm trying to say is, what makes an acid? How do we recognize an acid? What makes a base? How do we recognize a base? And we're going to look at more detailed chemistry. So what I've got up here on the board is just basically a little introduction here. And we've spoken about in our daily lives. We've encountered many examples of acids and bases. And I've just put a couple up here for you to have a look at. Some of them will be very familiar. For example, hydrochloric acid. You've probably used hydrochloric acid quite extensively in your school career. Sulfuric acid, nitric acid, in the school laboratory, lots of nice chemical reactions associated with those. But then here too, that you may have heard of, or you may not have heard of, that are very common acids that you actually can get very easily from everyday life. The first one is acetic acid, which is just another name for vinegar. And where do you get vinegar from, guys? Well, vinegar we see on chips, and we add it to salads to make salad dressing and things like that. And we all know that vinegar's got that very, very sharp taste. And this one over here, guys, phosphoric acid, is basically the acid that's found in Coca-Cola. So that's why when people say don't drink a lot of Coca-Cola, why not? It's not because there's so much sugar, sure, that's not good for you, but because there's an acid in Coca-Cola. And what does the acid do? It can react. And what it does, it actually reacts with the enamel of your teeth. And it can actually cause your teeth to rot. So if you know someone who drinks a lot of Coca-Cola, guys, you can go and warn him, be careful, his teeth will rot, he will have problems.
Bruce,
yes,
talking about the brown stuff that we're talking about now, apparently if you use Coke, paramedics even use it.
Sorry?
Paramedics use it to help at accident scenes because it helps get rid of things on the accident scene.
Yes,
so, yeah.
it does. Coke can actually be used very, very
for
efficiently
cleaning
in
materials.
That. It can be, because it can actually start to take away a lot of sort of rubbish that's lying around. Little experiment you can do, if you get some Coke, get an old coin, drop an old coin into the Coke, leave it overnight. Have a look at it the next day. Beautifully shiny.
Sparkling. I should do that with my jewelry.
Yeah, but there's also another bit more card thing to do. If you get a piece of meat, a piece of raw meat, put it in the same glass, look at it the next morning. It's not very pretty.
Oh, but it's fun experiments to do.
It's fun experiments, but it just shows you the acidic properties of Coke. So guys, there we now have it. There's some examples there of Coke. Of acids. I've also put two very useful examples of bases there as well. Caustic soda, which we all know as drain cleaner, is a substance called sodium hydroxide. There's the formula, NaOH. And this guy over here, ammonium hydroxide, we often find in Handy Andy. It's the active cleaning agent in Handy Andy. So bases are often used as cleaning agents, and we find those all around us at the moment. But as I said earlier, now that we've looked at a couple of examples of acids and bases, we now have a look at this question over here. What makes an acid, and what makes a base a base? And this is where now we're now going to get the meat of the reaction. Of the topic. We're now going to look at it carefully, and we're going to look at now the distinguishing characteristics of it. To give you guys a clue, I'm going to go, before we start looking in great detail, I want us to have a look at the chemical formulas of these acids and bases that we've got here. Hydrochloric acid, HCl. Sulfuric acid, H2SO4. Nitric acid, HNO3. Acetic acid, quite complicated, a bit of a complicated structure, CH3COOH. And phosphoric acid, H3PO4. Okay? Compare that to our bases over here, which are NaOH and NH4OH, sodium hydroxide and ammonium hydroxide. And at this stage, hopefully you'll be able to see something that's sort of consistently repeating through that might give us an indication or a hint as to what makes an acid and what makes a base. Okay, so have your thoughts. Let's go and do the theory. Let's see what you come up with, and let's see how many people agree with their ideas. So what we're going to have a look at now, and I'm taking it right up to the top here, are what we call our acid-base models. Now, guys, in science, when we talk about a model, what we are talking about is a representation of a particular thing. For example, if we're talking about an acid, how do we represent an acid? If we're talking about a base, how do we represent a base? What makes them characteristic? What sort of reactions can they undergo? And that allows us to draw up what this term is known as, or what we call a model. Okay, so guys, what is an acid? Well, an acid, according to our first definition, which was represented by a Swedish scientist by the name of Svante Arrhenius, 1887, so it becomes known as the Arrhenius definition. He said that an acid releases a hydrogen ion into a solution. Okay, an acid releases a hydrogen ion into a solution. So when we go back up and we look, and let's see if you guys were correct, can you see now that if we look at, let's get a nice color pen here, let's do that one. Can you see that with our acids, we seem to have a lot of hydrogens? Okay, I'm just going to circle those, and a hydrogen over there. We've got a common element that seems to precipitate itself through the actual formulas, the presence of hydrogen in the formula. So that's what Arrhenius actually jumped onto. And he said an acid will release a hydrogen ion into solution. So if I take hydrochloric acid over there, HCl, what actually happens is that hydrochloric acid undergoes a process known as ionization. I'll write that down. Okay, ionization. And what that ionization does is that it allows for the molecule to break up. Okay, remember guys, HCl is a covalent molecule. It allows it to break up into individual ions. So we're going from a covalent molecule to ions, and therefore we call that process ionization. And it releases a hydrogen ion into the solution. Now, let's think quite carefully before we move on. What, in actual fact, is a hydrogen ion? Well, if we think about hydrogen and its position on the periodic table, hydrogen, if we write down the AZ notation, is H11, which means it's got one proton in the nucleus and there's one electron orbiting around that nucleus. If we take away that electron, what are we actually left with? We are left with a proton. So the hydrogen ion itself is simply a proton that is found present in the actual solution itself. Okay. Now, the big question is, can protons exist by themselves in solution? And this is what Arrhenius now had to start thinking about. He's made the statement, he's identified that acids will release hydrogen ions, which are protons, into the solution, but can they actually exist? And the answer was, or is, no. Arrhenius discovered that the proton is not able to exist on its own. And straight away, it starts to look to combine with something else. And what it actually does is that it combines with a water molecule that is part of the solution. Okay, so when we're talking about these solutions, we're talking about aqueous solutions. They are acids dissolved in water. And what actually happens is that we form this particular substance there called H3O+. So in other words, that hydrogen ion adds to the water. We increase the number of hydrogens to 3, but now because of that charge there, we must have an overall charge on that. And this is known as the hydronium ion. Okay, so when acids dissolve in water, according to Arrhenius, we produce hydronium ions in the solution. And the hydronium ion is equivalent to say, well, it's the hydrogen ion in all seriousness. Okay, so that is now Arrhenius's understanding of what an acid actually is. So what he was able to do was to say, okay, if that's true, then we are able now to include water in the reaction of the acid when we add the acid to water. So we take HCl, the hydrochloric acid, we add it to water, and we produce the hydronium ion and obviously the residue, the leftover chloride ion in solution. And this is known as the Arrhenius equation for acid ionization. Acid ionization, the ionization of the HCl molecule to form an H3O+ hydronium ion and a chloride ion in solution. And that is how hydrochloric acid exists when it's in a bottle, when you buy the bottle of hydrochloric acid and it's put into your school laboratory. Also remember, guys, we can also get hydrochloric acid fairly commercially as well, especially if you've got swimming pools at home, because we need hydrochloric acid to adjust the levels of pH. And we'll talk about pH probably a little bit later on. Adjust the pH levels in the pool to make the pool nice and safe for swimming, and also to keep the algae away, especially during summer. So let's practice now. I've put a couple of little examples here. Let's pull them up. Where I've got what happens now when we've got H2SO4. Well, what happens with H2SO4? As we know, we're going to undergo ionization. Because there are two hydrogens, okay, we can produce two hydrogen ions, okay, plus a sulfate ion like that, okay. But remember, guys, that hydrogen ion is going to react immediately with water. So what we can do is write this down as H2SO4 plus H2O will give me two, whoopsie, I just want to just neaten that up a little bit for you like that. And we've got an arrow there, gives us two H3O plus SO4 2 minus, and I need to make sure that I balance it there as well. So can you see now that sulfuric acid is able to release two hydrogen ions, which means now that we need two water molecules to form two hydronium ions and the sulfate ion as the residue. Okay. What about the nitric acid? Well, nitric acid, can you see it's only one, so it's very similar to the hydrochloric acid. It will release H plus and NO3 minus. That will react with the water. So what do we now have is nitric acid plus water to give me one hydronium ion plus the nitrate ion that's present there. And then our guys, and I'll just underline them nicely for you, are our two ionization equations, according to Arrhenius, that now shows how we ionize acids in solution. And it's the presence of these hydronium ions in solution that makes an acid an acid. That's the important thing. Okay, hope you guys have got that. Just to carry on with a little bit more over here. As I put here in the blue writing, thus an acid will increase the hydronium concentration in water. So the more acid we add to water, the more hydronium ions we are going to be producing, and the more hydronium ions we produce, therefore the stronger the acid, or more concentrated the acid, should I rather say. Okay, now let's have a look at a base. Now, a base is actually very simple. In fact, it's much simpler than explaining the acids. And Arrhenius didn't have too much of a trouble trying to sort this one out. Because what did he say? He said a base will simply release a hydroxide ion into solution. So we go all the way back and look at our formulas for our bases. Can you see now that every base we've got there, or the bases I've got there, have got the OH group present? In other words, the presence of the hydroxide ion. So what happens is that all we simply do is we take the sodium hydroxide, we place it into water, and we simply get what is called a dissociation. We get a dissociation. Notice now, we're not talking about an ionization. An ionization takes place when you have a covalent molecule forming ions. Here we have an ionic substance, sodium hydroxide, sodium cation, the hydroxide anion. It's an ionic substance. All it's doing in the presence of water is breaking up into its individual ions. So we call that a dissociation. So if we have a look at other examples, what can we do? Very simple. All we have to do is look at the next example, which is ammonium hydroxide. When we spoke about that, that's in handy. Ammonium hydroxide will simply break up into the ammonium cation plus the hydroxide anion. And the next example, potassium hydroxide, will simply dissociate into the potassium cation and the hydroxide anion. And guys, can you see now? There is the Arrhenius base. The Arrhenius base is telling us that we are going to be releasing hydroxide ions into solution. Okay, so to summarize the Arrhenius definition, which is our first attempt at an acid-base model, remember 1887, a long time ago, what did Arrhenius say? He said, acids will release hydrogen ions into solution. The hydrogen ions will immediately react with the water because they're simply protons, and therefore protons, very reactive, can't exist by themselves, and we form hydronium ions. Bases will simply release hydroxide ions into solution. Okay, and that's what makes a base a base. However, there was a slight problem, and I've put it over here. There was a limitation. In other words, the Arrhenius definition, the Arrhenius model, had a flaw. And what was that flaw? Well, very importantly, it could only explain acid-base reactions of substances in solution. It could not explain acid-base reactions in other phases. And that was the problem with the Arrhenius definition. Now, obviously, they had to now modify it. Someone had to go out there, someone had to go and think about it, someone had to come up with a better idea. And guys, in the 1920s, there was a breakthrough in the understanding of acids and bases. That was an improvement on the Arrhenius model. It allowed for the understanding of acids and bases beyond just simply in solutions. And it allowed for acids and bases, base reactions, or rather say, to take place between gases, but take place between gases and liquids, between gases and solids, between solids and solids even. And we can find now that acid-base reactions can occur through all the phases. And the two scientists were named Bronsted and Lowry. And when we come back from the break, Indiana, I'm going to chat a little bit about the Bronsted-Lowry theory, the Bronsted-Lowry model for acids and bases.
Fantastic. Okay, guys, so I hope you've all been listening to Bruce and you've been riveted and you've been taking down notes and paying attention. I just wanted to give Liberty a big shout out and a big thank you for making this awesome show possible. Don't forget, guys, to get those questions in, because especially during these breaks, it's a nice time for me and Bruce to chat about things that you guys aren't understanding. So do that now. Get yourself a glass of water, have a little relax, and we'll see you now after the break. Hi guys, and welcome back to Learn Extra Live. This is Physical Science Grade 11. So guys, I hope you're tuning in and I hope you're all posting on the Facebook page, facebook.com/Learn Extra. Also chat to me on Twitter @LearnExtra. We're also giving away a Casio calculator, and the way you get that is by commenting and posting, and most of all, helping each other out on the Facebook page. And without further ado, I see Jürgen. You want to know, what about the Lowry-Bronsted theory? We're getting right to that. Bruce? What about it?
All right, thanks, Indy. Right, the Lowry-Bronsted theory, or the Bronsted-Lowry theory, which one comes first? Well, that's always been a bit of a historical debate, because Bronsted and Lowry, or Lowry and Bronsted, they simultaneously came up with the same ideas. They didn't work together, guys. They were actually in separate laboratories at separate universities. They came up with the same idea. They published their papers almost simultaneously, and because they came up with these ideas so close together, they decided to acknowledge and honor them with the name of Bronsted-Lowry or Lowry-Bronsted. It doesn't really matter, but most textbooks always refer to it as the Bronsted-Lowry model for acids and bases. And as we said before the break, or as I said before the break, what we are looking at here, guys, is now the upgrade, the improvement on the Arrhenius model. Because the Arrhenius model, remember guys, could not explain acid-base reactions that occur in between different phases. It could only explain solutions, acids and bases in solutions. So, what did these two great scientists come up with? Well, as I've said here, it was developed simultaneously and allowed us to improve with the Arrhenius model. So what they had to do, they had to redefine exactly what an acid and what a base was. Now, or should I say is. Now, you'll remember what Arrhenius said. He said that an acid will release a proton, okay, will release a hydrogen ion into solution, and a base will release a hydroxide ion into solution. What they did, they said, hang on, let's look at this completely differently. What they did, they said, let's now define acids and bases in terms of their ability to donate or accept protons, or, in other words, hydrogen ions. There's now no mention of hydroxide ions in this particular new model, this particular new understanding. So what they were able to do is able to define an acid and a base in a completely different way. And what was that? Well, an acid, they said, is a proton donor. It's going to donate a hydrogen ion. And what is a base? A base is a proton acceptor. It's going to accept a hydrogen ion. So that particular statement then allowed for acid-base reactions based on the movement of protons between substances. It allowed them to be used in all different phases. And this was known as protolysis. Protolysis. Okay, and there's a word that is important for you guys to get down. Protolysis simply means the transfer of protons. And that's what we're going to be having a look at in this model. So, what we're going to do now is have a look and see how this works. So, an acid is a substance that releases hydrogen ions from its structure, and a base is a substance that accepts hydrogen ions into its structure. So, let's have a look at a very familiar example. Now, a lot of you guys will probably look at that and say, but hang on. We saw this in the Arrhenius model, but isn't this Arrhenius supposed to be outdated and doesn't work? Now, no one said Arrhenius was wrong. It's just that he needed a better model to explain things. So we can certainly take examples from Arrhenius and apply it and modify it and upgrade it to the Arrhenius thinking. So, let's take now our example and let's see what's happening in this example itself. We'll just take the first one. Well, we're now looking as an acid as a proton donor and a base as a proton acceptor. So let's now look at the reaction and let's try and track the movement of protons in this particular reaction. Well, let's have a look and see what happens. Well, here's HCl, okay, and we can see now there's a proton, okay, a hydrogen ion that will be ionized from the hydrochloric acid. And what will happen now is that it's going to react with water. Can you see now what's happened is that that hydrogen, okay, has now moved, it's reacted with water, and it's now produced this hydronium ion. So therefore, what's happened now is that the HCl, the hydrochloric acid, or hydrogen chloride molecule, okay, has donated a proton. So therefore, this must be, according to Lowry and Bronsted, that must act as an acid. It's donating a proton. But now, what is this guy doing at the moment? Well, this guy is now taking the proton to form the H3O plus. Okay, so therefore he is accepting, the water is accepting the proton. So therefore he must be acting as the base. And there, guys, is now where we come up with this modern theory of an acid-base reaction. This acid-base reaction is a simultaneous reaction that occurs through protolysis. In other words, the transfer of protons. One substance is donating the protons, one substance is accepting, and they both must occur simultaneously. And that's very important. We can't have something donating a proton without something accepting it. And there's nothing can accept a proton, if you look at it the other way around, nothing can accept a proton unless there's something donating it. So there have to be two different molecules in the system, two different substances in the system, an acid and a base. We're going to form our hydronium ion, and then we've got this little guy over here, the chloride ion. Where does that come from? What does that represent? Well, that simply represents the leftover residue from the hydrogen chloride. So the important thing is now, have we been able to identify our acids and bases in the reaction according to Bronsted and Lowry? Yes, we have. Proton donor, proton acceptor. Let's look at other examples. Over here. Okay? What have I got here? Well, I've got HCl plus NH3, hydrogen chloride plus ammonia gas. Okay? Now, what is that producing? Well, it's producing NH4 plus Cl minus. Okay? And NH4 plus, that's the ammonium cation. And there's the residue chloride ion from the hydrogen chloride. So, what's happened again? Well, can you see that this proton, okay, has now joined onto the NH3 to form the NH4, okay? And in other words, the NH3 has accepted that proton to make the NH4 as well. So what have we got? Again, we've got acid, okay? The HCl is acting as an acid. The NH3 here is acting as a base. Okay. All good? That should be fairly straightforward. Right. Now, let's see what's happening over here. H2SO4, exactly the same thing. However, two protons to form two oxonium ions. So there, that must be my acid again. Okay. And this, again, is accepting to form my hydronium ion, which is going to be my base. And we've now got two hydronium ions, and there's the residue, the sulfate ion from the sulfuric acid. So guys, can you see now how we are identifying our acids and our bases? Not through hydrogen ions and hydroxide ions now, but through whether something is able to donate protons, hydrogen ions, or something is able to accept protons, or the hydrogen ions. I hope that makes sense to you guys. Are there any questions that have come in about the Bronsted-Lowry model at this stage?
Let me have a look at the Bronsted-Lowry. Nothing at the moment. Jürgen is talking about it. He did kind of put a little explanation on the page, which is quite cool. So guys, carry on doing that. There's nothing on that particular section at the moment. I do have, I don't know, maybe you can tell me yes or no, but this one's from Revalisha, and she says, can you please explain the standard solution and concentration calculation?
Yeah, we'll try and do that at the end.
Okay, well, there you go. Yeah.
All right, I'm just trying to get through the basic understanding of the acids themselves.
Okay, so that you carry on, Bruce, carry on.
Great. Yeah. Well, guys, hopefully we're all comfortable with that. Okay, and if you aren't, please drop us a line on the Facebook page, and we'll try and get to these questions as quickly as possible. Okay. Now, once we're able to understand these particular movements of protons in terms of our acids and our bases, we can develop the Bronsted-Lowry theory a little bit more. In other words, we can now start looking at the reactions and start looking at the specifics of the reactions in terms of the movement of these protons, and we're going to now look for what we call acid-base pairs. Okay, so what we're going to have a look at, and I'll just read through this with you. It says, when we consider the Bronsted-Lowry acid-base model, we often see that the acid-base reactions are reversible, and we're going to talk about those now. That is, reactions can either go forwards or in the backwards direction. Now, guys, I'm not too sure whether you've had much experience or much classroom chat about reversible reactions. But reversible reactions are reactions that are able to move forwards and backwards. And a lot of acid-base reactions are able to do this. Okay, I know in grade 12 that you have a very careful look at reversible reactions when you do a section called chemical equilibrium. But at this stage, all I want you to understand from my side is that acid-base reactions can go forward, which is basically from left to right, or they can go back, which is basically from right to left. And because of this, we are able to identify something called an acid-base pair within the reversible acid-base reaction. So let's pull these up a little bit over here. Okay. So if we have a look at the reaction, we can see quite easily that the hydrochloric acid will act as the acid. We know that. Okay. And we can see now that the ammonia there is going to act as the base. Remember, guys, how we did that? This is the proton donor. That's the proton acceptor. How did I know that? I knew that because of the formation of the ammonium cation and the leftover chloride anion, which is now without its hydrogen. Okay. However, if we look at the back reaction, now we go backwards. What do we notice about the back reaction? Well, which one is now the proton donor and which one now is the proton acceptor? Well, if we have a look at NH4 going backwards, NH4 goes to NH3. Can you see now that NH4 is losing a proton? So in the back reaction, and we'll change the color for that. What'll be good? Shall we try purple? That will. Oh, I don't think that's going to be seen too well. Yeah, let's try a better color. Let's try red. I'm sure red will stand out. That is going to act as an acid in the back reaction. Therefore, if that's now going to donate a proton, what is now gaining the proton? Well, the chloride must gain the proton to go back to HCl. So now we've got a base. Chloride ion is acting as a base in the back direction, or reverse. Sometimes we call it the reverse direction. So guys, can you see now that we're going to start linking up our forward and back reactions, and from there we're going to try and now identify acid-base pairs based on the forward and back reactions. So, how do we do that? Okay. Well, can you see now that we can link up certain substances, certain compounds from here? For example, HCl and Cl minus. Now, if we go back over here, can you see now that HCl and its residue Cl minus, when it goes forward, okay, it's acting as an acid. When it goes back, the Cl minus is acting as a base. Therefore, we can link those two up, and we can see acid-base. Same with the NH3 with the ammonia. Okay? In the forward reaction, it's acting as a base. In the back reaction, the NH4, which was produced originally, is losing the proton and is acting as an acid. So therefore, those two are related. And what we do when we now make acid-base pairs is that we can link these acid-base pairs up. So we've got HCl, okay, and Cl minus as one acid-base pair, okay, and we've got NH3 and NH4 1 plus as another acid-base pair. Can you see now that the acid-base pairs are similar to each other, but they differ by one proton? I'll say that again. Can you see now that the acid-base pairs are similar in structure, but they differ by one proton? And that is a very easy clue to try and establish and identify an acid-base pair. So, let's have a look. There they are. Can you see now, if I take them out of the equation, HCl and Cl minus, can you see now that they are very similar? HCl acts as an acid in the forward reaction, Cl minus acts as a base in the back reaction. So there now becomes acid-base pair number 1. Okay? So I'm going to put A1 there, and I'm going to put B1 over there. There's my first acid-base pair. Let's have a look now at my second acid-base pair. NH3 and NH4 1 plus. Can you see, guys, we are differing by one proton again. So therefore, he acted as a base in the forward. Therefore, he's acting as an acid in the back, or reverse reaction. So that's going to be base 2 and acid 2. Okay. The 1s over here represent acid-base pair number 1, and the 2s represent acid-base pair number 2. And guys, according to that Bronsted-Lowry model, okay, you will always have 2 acid-base pairs within that reaction. Okay, always 2. And very easy to pick up. All we simply have to do is find the 2 chemical species, the chemical substances that are similar but differ by one proton. And then you can be able to link up your acid-base pairs. Okay. Now, a little bit more terminology coming your way. These acid-base pairs are similar but differ from each other by one proton, and thus are known as conjugate acid-base pairs. Guys, the word conjugate simply, in a nutshell, explains what I've just said about differing by one proton. So we talk about the word conjugate acid-base pairs. How do we introduce that into the terminology? Well, if HCl acts as an acid, then the Cl minus is the conjugate base. It differs by one proton. And if NH3, the ammonia, is acting as the base, then the ammonium ion, the NH41 plus, is the conjugate acid. So guys, our acid-base pairs, we can actually now just modify slightly and call them conjugate acid-base pairs to explain the difference of one proton. I hope that makes sense, but we are going to try and practice a little bit here and see if we can look at some examples. So if I take this example over here, and my question to you guys is, can we identify my conjugate acid-base pairs? Well, let's have a look at the reaction. Well, can you see now it is reversible? You see the double arrows? Okay, we've got a forward reaction, we've got a back or reverse reaction. So let's have a look at the forward reaction first. NH3 plus H2O. The NH3, okay, goes to form NH4. So that's now gaining a proton. The H2O is going to form OH minus. Can you see that guy is losing a proton? So the H2O here is acting as an acid, and that is acting as a base. Okay? Now, what are they basically similar to? Well, can you see now that this guy and this guy are differing by one proton? So we can link those two up like that. Okay? So if this is acting as a base, and I'll put this in red here, if that's acting as a base, and let's make this our first acid-base pair, then that must be the conjugate acid for that particular base. So therefore, in the back reaction, he will be acting as an acid, a proton donor. So there now is an acid-base pair, my first acid-base pair. The water is acting as an acid. It's losing a proton. It's going to form OH minus. So therefore, we can link those two up like that. Okay? And if this guy is acting as the acid, I'm going to make this A2 because it's my second acid-base pair. Then that has to be the conjugate base for this particular acid. So therefore, we have A2 and B2. And there we now have our acid-base pairs in that particular reaction. Okay, let's try one more. It's always good to practice these as much as possible. Right, NH41 plus F minus, the fluoride anion forms hydrogen fluoride, or often known as hydrofluoric acid, very nasty stuff, and ammonia. Right, let's have another look. Okay, NH41 plus to NH3, can you see those are similar? They differ by one proton. He is now losing a proton, so he has to be an acid. So I'm going to put A, and that must be the conjugate base. So that's A1 and B1 for my first acid-base pair. So I can link those two up like that. And there must now be a second acid-base pair. Well, this guy is gaining a proton to form HF, so he must be gaining. So he's a proton acceptor. So he must be a base. He must be my second, and this must be my acid, and there's my second acid-base pair, like that. Okay, and very quickly, for the last one over here, I'm hoping that you've picked up the pattern. HNO3 plus H2O gives you H2O plus NO3 1 minus. Here, these two must be linked. Okay, this is going to be A1, and that must be B1, my first acid-base pair. A1 and the conjugate base. And then we've got these guys over here. This must be acting as a base. Let's call that B2, and that will be A2, and there's my second acid-base pair, like that. Okay, so guys, can we see now how simple it is to actually identify our acid-base pairs? Okay. Indy, are we going to take a break? Or
yes, let's take a break so I can go over all the questions on the page. Guys, please get those questions in. Don't forget we will be taking those questions in the last part of the show. It's very, very important that they are relating to the topic that we are talking about. Without further ado, let's take a little break. See you now. Hi guys, and welcome back to Learn Extra Live. This is Physical Science Grade 11, and it's Bruce and Indy tuning in with you. We have got into our last 10 minutes of the show. So what we're going to do, guys, is we're going to try and answer your questions in the last 3 to 4 minutes, and we're going to let Bruce carry on with this lesson. Bruce, take it away.
Cool. Right. Got a few more things to cover, so I'm going to go over it quite quickly. But we've had a question that came up and said, a question about an ampholyte or an amphoteric substance, and it's exactly what I'm actually moving on to now. So whoever asked that question there, Indy, we're going to answer that right now.
Awesome.
for that person. Okay.
Fantastic.
Guys, what we're going to have a look at is that when I did identified my acid-base pairs on my equations that I've done here, I want you to notice something about water. Okay? I want you to notice water in that reaction and water in that reaction. Hopefully something's jumping out of you at this stage, and that is that in this reaction over here with NH3, water is actually acting as an acid. Yet, when it reacts with HNO3, with nitric acid, it actually acts as a base. Now that is quite unique. We've got a single substance which is either able to act as an acid or a base. And guys, these substances do occur. Okay, they are known as ampholytes, and I made a short little note over here for you. And basically what they do, or ampholytes, is that they have the ability to act as both an acid and a base. In other words, they've got a very special property. Not all substances are ampholytes, guys. Okay, only certain substances are, and the most common one is water, H2O, as I showed you in that reaction. So when we talk about these substances, we talk about them as ampholites, and therefore we say that they are amphoteric. Okay. Now, quite big words, quite big terminology, and so we're just going to make sure we do understand and we're able to pronounce them properly and we're able to put them down on paper. We talk about an ampholite, a substance that can act as an acid and a base, and therefore we say that that substance is amphoteric. So ampholite, amphoteric, both those words are acceptable to explain the phenomenon of certain substances being able to act as both acids and bases. Okay, how do we identify it? Well, when we do our acid-base pairs, or acid-base conjugate, or conjugate acid-base pairs, we can then see it from that particular linking up, and we can see, aha, just like we had over here, look at that. Here, water's acting as an acid, yet over here, water's acting as a, water's acting as a base. All right. So guys, please make sure that we have got this under control. It's very important. I know they like to test acid-base or conjugate acid-base pairs. They like you to identify, link them up, and to identify any ampholites or amphoteric substances in the actual equations. So guys, quite an important little heads up for you on that one. Okay, but as we move into the last part of the show, there's just one short little thing I would like just to quickly do with you guys, and we're still under acid-base reactions. And I want to talk about what happens when an acid and a base, acid as in a, for example, hydrochloric acid and a base in terms of a hydroxide are able to react together. And we introduce a reaction which is known as neutralization. So when an acidic substance and a basic substance act or react together, we have a neutralization reaction. Now, what do we mean by a neutralization reaction? Well, a neutralization reaction is a reaction that will remove both the acidic and basic characteristics of those substances. So in other words, it destroys the acid and it destroys the base. What do we get out of it? Well, we produce a substance known as a salt. Okay. Now, we've got to be quite careful with this word salt, because we use the word salt fairly generally and fairly sort of easily when we sprinkle our salt onto our food, when we have supper and things like that. But guys, what is salt? Well, everyone knows that salt is sodium chloride. Okay? And we can make sodium chloride by reacting the acid hydrochloric acid and the base sodium hydroxide, and we will form sodium chloride, and we also get another residue which is simply water being given off. NaCl, sodium chloride, is an example of a salt. Okay? Because what is a salt? A salt is a general name given to all products formed from an acid-base reaction. So it's just by coincidence that hydrochloric acid plus sodium hydroxide produces sodium chloride, and that is what we define as table salt. Okay, but we must have a look at other reactions, because if we look at other examples over here, sulfuric acid plus potassium hydroxide is going to produce potassium sulfate plus water. Okay? Yes, and I put the balancing in there, so yeah, we do need a 2 over there to balance it out. Now, what is potassium sulfate? Well, that's also a salt, guys. Okay. It's also a salt. Why? Because it's a product of an acid-base reaction. Now, do we sprinkle potassium sulfate onto our food? Absolutely no ways. So, guys, please, we must get away from thinking that when we talk about salts, we're talking about the stuff we sprinkle on our food. A salt is simply the general name or general term that we give to the product of an acid-base reaction. Another example I've got over here. What about nitric acid plus ammonium hydroxide? Well, that will produce ammonium nitrate also plus H2O. Okay? And that is balanced as it stands. There, guys, is another example of a salt. Ammonium nitrate is a salt. It's a product of an acid, there, the NO3 part from the acid and the NH4 part from the base, and there it is, the base residue and the, whoopsie, that moved around a little bit. Let's just go back there.
Easiest thing to do.
Okay, that doesn't want to do it. Doesn't matter, we almost finished this, but we've got, there's our production, there's our salt over there. Okay, and what we have got right at the end, just to conclude this lesson, is to chat about our general formula, or general equation, shall I rather say. Acid plus base will always give us a salt plus water. So if you're studying a reaction between an acidic molecule and a basic molecule, okay, or should I say acidic compound and a basic compound, you will know that you will always get a salt and water as a product. Okay. Anyway, that's all I've got. Now, I know there are some questions and we're running out of time, so I want to quickly have a little chat about that.
Let's see how many we can go through really fast. And hopefully, Bruce, I will be able to choose some good questions and not some bad questions.
You go for it.
Let's try. Okay, so this one's from Mfiwe, and she says, or he, sorry about that, says, how can an oxygen atom bond with 3 hydrogens when only it has a valency of 2? And I think we were discussing this earlier. Somebody else was wondering the same thing.
That is something called a dative covalent bond. Okay, and a dative covalent bond is something you should have maybe have done earlier on in this year when you looked at atomic combinations. Okay, it's quite a specific type of bonding, all right, but it allows for the formation of, or should I rather say 3 hydrogens to be attached to 1 oxygen instead of only 2 hydrogens. Okay, so the question's very good because it doesn't make any sense. However, we have this thing called a dative covalent bond, and very quickly, if I had to draw it for you, like this, and this is now, remember we've got lone pairs on the oxygen like that, is that the hydrogen ion comes in, and the hydrogen ion actually steals, in a way, in inverted commas, steals the electrons from the lone pair of the oxygen, and therefore we can get that. However, it will have a positive charge because that H is bringing in a positive charge in there. We've got to keep our charge balance. So that's how it happens. Very quickly.
Now, hopefully this is a quick one, and I think it might be our last. This one's from Michael, and he wants to know, must the chemical formula be balanced?
No, the chemical equation must be balanced. Okay. We must have a balanced chemical equation. The chemical formula you must be able to write down as well, because if you write down the wrong chemical formula, then you're not going to be able to balance the chemical equation. Okay, so it's a little bit of, you're between a rock and a hard place here. You've got to make sure that your chemical formula is correct, otherwise it's going to throw the entire chemical equation out. Stuff that's so important from grade 10, guys. Okay, if you haven't picked up chemical formula writing, please go and revise your grade 10 notes.
Okay, so Bruce, I think we've actually run out of time, unfortunately. I know, guys, there are so many questions on the page, but you know what? You guys are helping each other out fabulously. I know there's Jürgen Govender. You have been rocking it. Dude, he's been helping everyone on the page with all of their answers, and he's been completely great. So grade 11s, you guys have completely rocked. You've been awesome. I've had such a fun time. If you do have any questions, pop them on the page. We'll try and help you out. If not, mindsetters, please help us out too. Grade 12s, don't forget that you are next. Grade 11s, see you same time, same place next week. Bye.